this video, we're going to look at the hydroxide ion promoted amide hydrolysis. So whenever we have a hydrolysis of a carboxylic acid derivative, the product is going to ultimately be the carboxylic acid or maybe the carboxylate salt, depending on the pH. So let's take a look at this. So if we're looking at an amide, we could have something with this general structure. And so we drew a primary amide, but you could also replace these hydrogens with R groups. If you replace it with 1, that would be a secondary amide, or 2, then it would be a tertiary amide. All right, so we have, like I said, just a primary amide here. So we're gonna do the hydroxide ion promoted amide hydrolysis. So if we wanna get to the carboxylic acid product, we're going to use, say, an aqueous solution of sodium hydroxide, and you really need to heat this up to get it to work. And then in a workup step to get to the carboxylic acid rather than the carboxylate, you would add in some aqueous acid. Okay, and so if you're predicting the product of something like this, predicting the product is fairly easy, because whatever is attached to your nitrogen is going to ultimately be your leaving group, and you're going to be replacing it with a carboxylic acid, so with an OH to form the carboxylic acid. So whenever you are doing a hydrolysis of a carboxylic acid derivative, your product is going to be the carboxylic acid or maybe the carboxylate salt, just depending on the pH of the solution. Okay, so let's look at an actual example. Let's start replacing these R groups with things that are a little bit more complex so you can see how this applies to, say, a real system. So maybe let's start with, so we draw a benzene ring, and I'm gonna make an amide, and maybe I'll put a methyl group on there. Okay, so if we wanted to name this, this is N-methyl. So that tells us that we have a methyl group attached to the nitrogen. And then the amide is the amide of benzoic acid. If this was a carboxylic acid, it would be benzoic acid. So this is N-methyl benzamide. So if we go through this two-step process, so heating it up with aqueous base and doing an acidic workup step, then this would give us benzoic acid. So we would get the carboxylic acid, and you would also have the salt of that amine. So we would have that salt, okay? And if we didn't do the acid step, so if we didn't do that, we would have the carboxylate and we would have the neutral amine. So this would be protonating everything in that last step. All right, so let's take a look at this mechanism and how it works. And if you watch the video on the acid catalyzed hydrolysis of amines, you would have noticed a lot of steps. In the base catalyzed or base promoted reactions, there's not as many steps. And we say base promoted rather than catalyzed because it's not actually acting as a catalyst. You actually consume the hydroxide in this reaction. All right, so let's draw the starting material. And so these base promoted processes are always shorter mechanistically. Now, in the lab, it might actually take longer for this reaction to go, but when you're drawing the curved arrows, it's actually a lot faster to draw the curved arrows for a base a reaction in basic solutions. So you've got the hydroxide, which is going to be your nucleophile, and it is going to attack the carbonyl carbon and push the electrons up onto the oxygen. Okay, and we get our tetrahedral intermediate, right? So we always call it a tetrahedral intermediate because we're going from a trigonal planar carbon to putting 4 single bonds on that carbon and making it tetrahedral. And so we have the amine still on one side, and then we have the hydroxy group that we just added. So at this stage, we're used to seeing, let me move this up so you can see it. We're used to seeing this collapse and kick off a leaving group. And that's why this is an equilibrium. So if this were to collapse and kick off a leaving group at this stage, the better leaving group would actually be the oxygen that you just added, because you'd be forming an anion on oxygen which is a weaker base than an anion on nitrogen. So to have this reaction move towards the product, you actually have to be in really basic solution, basic enough that you actually pull off this proton. So we're going to use another equivalent of hydroxide, and we're going to remove this proton. And so what this does is it's going to form actually a molecule with an overall 2 negative charge, right? So we're in really basic solution for this to happen. But now we can explain how we're able to kick off the nitrogen as a leaving group, because now we don't have any other leaving groups. You're not going to kick off an oxygen with a 2- charge. So what we're going to have now is you can reform the carbonyl from either one of those oxygens. It doesn't matter. Both are equally probable. And then you're going to kick off the nitrogen as a leaving group. And it's really a terrible leaving group. But at this point, this reaction is not going to go backwards. So I'm just going to draw the arrow in one direction. So we've now reformed this bond, and we have the alkoxide, right? And then we also have the the base that we formed when we kicked off this nitrogen. So this is a pretty strong base. So even in just water solution, right? Because we did say that we were using aqueous base. As long as you have any water in solution at all, that water would protonate this to give you the amine. Okay, so I want to show this because after this step, this would be the product mixture that you would get if you did not do that aqueous workup. So this would give us just the carboxylate, and the neutral amine, so H2CH3. All right, and so this would be the products if you did not do that second step. All right, but typically you're going to go through and you're adding just enough aqueous acid to put a proton on here and here. So this would be your workup step. So this is your second step where you're adding H3O+. Right? And so we say it's a second step because it really is. Like, this whole reaction is done. You heated it to reflux. You maybe checked some TLCs. You made sure the reaction was complete before you added in a little bit of aqueous acid. And so we can show aqueous acid protonating both this carboxylate and this amine. So to save space, I'm just going to show both of these at the same time, though not to the same molecule of H3O+. So these would both be protonated, and then we would get that carboxylic acid and ammonium salt, right? And so again, this is the product as long as you do this acidic workup. If you don't do the acidic workup, this carboxylate and the neutral amine would be the product.